Today we will explore one of the greatest enigmas in the history of navigation, the secret technology the Vikings used to guide their vessels through the darkness, the fog, and the overcast skies of the medieval North Atlantic, crossing entire oceans without the instruments we consider indispensable today. Before continuing with the video, remember to subscribe to the channel for more documentary narratives like this one. In the heart of the North Atlantic, where the horizon merges with the grey sky and the damp cold penetrates every layer of fabric and wood, a seafaring people accomplished what seemed impossible. Without magnetic compasses, without modern nautical charts, without electronic instruments of any kind, men and women crossed hundreds and sometimes over 1,000 kilometers of open ocean, reaching precise destinations with a consistency that still surprises scholars today. This is the account of how the Vikings mastered the medieval seas and of the secret they preserved for centuries, kept within the depths of ancient sagas and the translucent crystals that emerged from the Icelandic earth. To understand the scale of this feat, one must step back in time and dive into an era very different from our own. We are in the 8th, 9th, 10th, and 11th centuries of the Christian era. Medieval Europe lives behind stone walls, candlelit monasteries, and fiefdoms surrounded by dense forests. For most civilizations of the time, the ocean is a frontier, the limit of the known world, a place of impenetrable mysteries and nameless dangers. But for the Scandinavian peoples of Norway, Sweden, and Denmark, those whom history would come to collectively call Vikings, the ocean is something radically different. To them, the sea is a path. The word Viking, derived from Old Norse, likely refers to the inhabitants of coastal inlets, the Vikingjar, those who dwelled in the sea arms that cut into the Scandinavian coast. It is from this intimate and ancestral relationship with the sea that one of the most extraordinary maritime cultures humanity has ever produced emerges. Even before the Viking Age began formally, conventionally marked by the raid on the monastery of Lindisfarne in northeastern England in 793, the Scandinavian peoples had already developed shipbuilding techniques that put them decades ahead of any other European civilization. Viking vessels were masterpieces of engineering for their time. Drakkars, slender and elegant warships optimized for speed, and knars, broader vessels that transported cargo, livestock, and settlers across Atlantic routes. Built using overlapping planking techniques that Norse carpenters mastered with expertise, these ships combined structural lightness with remarkable resilience, and the V-shaped hull allowed for both deep-sea navigation and entry into shallow rivers and estuaries. But all this sophisticated engineering would be of little value without the ability to navigate, to know where one is, where one has come from, and where one is going. On the open sea, far from any visible reference point on the coast, the navigator is reduced to themselves, the sky above and the water all around. It is in this environment of radical isolation that Viking navigation techniques reveal their true genius, accumulated over generations of direct experience with the most hostile seas in the Northern Hemisphere. The most fundamental of techniques was also the oldest, the observation of the stars. At night, when the sky was clear, Viking navigators oriented themselves by the stars with the same fluency with which an experienced reader scans the words on a page. The pole star, called in Old Norse Leidarstjarna the guiding star, was the primary reference point, due to its unique characteristic of remaining practically stationary in the Northern Hemisphere sky. By keeping the pole star in the same position relative to the horizon, the navigator ensured they were following the same line of latitude, advancing east or west without significant deviation. By day, the position of the sun, its arc from sunrise to sunset, its height above the horizon at noon, provided equivalent information regarding the vessel's direction and latitude. Beyond the stars, the Vikings read the ocean like a text filled with information. The water temperature, the behavior of seabirds, certain species rarely venture beyond a specific distance from land, the presence of algae and marine animals in specific areas, cloud formations and wind patterns, all completed an extraordinary repertoire of environmental reading. But there was a problem that none of these techniques could fully resolve. At the latitudes of the North Atlantic, especially on the routes between Norway, Iceland, and Greenland, a cloudy sky is not the exception, it is the rule. Entire weeks can pass without the sun or stars appearing. The fog is thick, persistent, and can emerge without warning. Atlantic storms are frequent and violent, and when the sky closes completely, navigation by the stars becomes impossible. The sun hides in a uniform and impenetrable grey, and the navigator who relied exclusively on celestial observation found themselves suddenly without a guide. This was the central problem of Viking navigation on the great ocean routes, and it is here that the true mystery of this story begins. How exactly did these sailors manage to hold their course for days and weeks on end, even when the sky was completely overcast? How did they consistently reach destinations located hundreds of kilometers away, sailing in conditions that would have completely disoriented most medieval sailors? For centuries, this question remained without a satisfactory answer. Historians and archaeologists knew what the Vikings had done: reach Iceland, colonize Greenland, and touch the coasts of North America almost 5 centuries before Christopher Columbus. But the precise mechanics of how they achieved these feats in such adverse conditions remained an enigma that resisted conventional explanations. There was something beyond the stars and the sun, beyond the currents and the winds, beyond the birds and the whales. There was a knowledge that scholars could neither see nor name. The answer was hidden in 2 unlikely and deeply interrelated places. The first was the ancient Norse sagas, the literary and historical texts that Scandinavian peoples used to preserve their histories, their values, and their knowledge across generations. The second was a stone, a translucent stone, modest and almost banal in appearance, found in certain regions of Scandinavia and in abundance along the coasts and beneath the soil of Iceland. A stone that, when held up against the light of a cloudy sky, revealed the invisible. The sagas are documents of extraordinary richness, composed mainly between the 12th and 14th centuries, but often describing events that occurred between the 9th and 11th centuries. They preserve a detailed portrait of the life, customs, travels, and values of medieval Nordic peoples. They are long, sophisticated texts, rich in practical and psychological detail, which modern historians have learned to treat not merely as literature, but as historical sources of primary importance, deserving of careful and rigorous investigation. In several of these sagas, there appears an intriguing reference to an object described in Old Norse as solarstein, literally sunstone. The saga of Saint Olaf, one of the most celebrated texts of medieval Nordic literature, contains one of the most specific and significant mentions of this object. The text describes a situation in which King Olaf II of Norway, who lived between 995 and 1030, and whom the Catholic Church would later canonize as Saint Olaf, the patron saint of Norway, consults a trusted navigator on how it might be possible to determine the position of the sun when the sky is completely covered by clouds. The navigator takes a special stone, looks through it toward the overcast sky, and is able to indicate with precision the exact position of the sun above the clouds. The saga describes the subsequent verification. When the sky clears, the sun appears exactly where the stone had indicated. For many years, most experts treated this reference with skepticism. The idea of a stone capable of revealing the position of a completely hidden star seemed to belong to the realm of legend and folklore more than to verifiable history. It was convenient to categorize the solarstein alongside other elements of the sagas, interpreted as magical or poetic. But some researchers refused this simplistic interpretation and decided to take the reference seriously, investigating whether there was any concrete physical basis behind it. To understand what these researchers discovered, it is necessary to make a brief foray into the world of optical physics, specifically the phenomenon known as the polarization of light. Sunlight, before reaching our eyes, passes through a series of interactions with the Earth's atmosphere. One of the most important is the phenomenon called Rayleigh scattering, named in honor of the British physicist Lord Rayleigh, who described it mathematically in the 19th century. When sunlight passes through the atmosphere, it collides with gas molecules which cause the light to scatter in all directions. It is this differential scattering that explains why the sky appears blue during the day. The frequencies of light corresponding to the color blue scatter much more efficiently than the other frequencies of the visible spectrum. But Rayleigh scattering has another less obvious consequence. Upon scattering through the atmosphere, sunlight becomes partially polarized. This means that the light waves coming from the sky tend to vibrate predominantly in a specific plane, determined precisely by the position of the sun. The plane of polarization is always perpendicular to the line that connects the observer to the sun. In other words, the direction of the sun leaves an invisible but systematic signature on the pattern of light that passes through the clouds and reaches the eyes of those observing the sky. The human eye cannot distinguish polarized light from non-polarized light. To our visual perception, the two are simply identical. But certain natural materials have the property of interacting in distinct ways with polarized light, depending on their orientation. When a piece of such material is rotated while observing the light passing through it, changes in light intensity become apparent, revealing information about the plane of polarization, which consequently reveals the direction from which that light comes, the direction of the sun. This creates a possibility of remarkable elegance. If the right material exists and the navigator knows how to interpret what they see, it becomes possible to determine the sun's position even when it is completely hidden behind clouds, provided those clouds do not block all light, which in practice rarely occurs. Some light always penetrates, and that light carries, encoded in its polarization, the signature of the sun's direction. The right material in this case is a mineral called calcite, specifically a variety of high purity and extraordinary transparency known as Iceland spar, or optical calcite. The name is not coincidental. Iceland houses one of the largest and purest deposits of this mineral in the world, and it was on the island's coasts and rock formations that it was found in greatest abundance by the first Norse settlers. Iceland spar has a fascinating optical property called birefringence, or double refraction. When a beam of light enters an optical calcite crystal, it is split into two separate beams, which emerge from the crystal at slightly different angles. Each of these beams carries a distinct polarization, perpendicular to the other, so that the crystal translates the invisible polarization of the light into a visible difference in brightness between two images. This property turns Iceland spar into a remarkably effective polarization detection instrument. When the navigator holds the crystal and rotates it slowly while looking at the sky, they see the two images projected by the crystal change in relative brightness continuously. At a specific angle of rotation, the two images reach exactly the same brightness, and this point of equalization indicates the crystal's alignment with the plane of polarization of the light passing through it. From this alignment, with knowledge of the relationship between the sky's polarization pattern and the position of the sun, the navigator can calculate the direction in which the sun lies, even without seeing it. The double refraction of calcite was formally described and documented in 1669 by the Danish physician and scientist Rasmus Bartholin, who observed the phenomenon in crystals of Iceland spar and recorded it in a scientific treatise. But Bartholin was, unknowingly, describing a property that had already been explored in a practical way centuries earlier by the navigators who crossed those same cold and cloudy seas, heirs to a technical tradition transmitted orally through generations of sailors. The archaeological evidence that most concretely confirmed the use of Iceland spar as a navigational instrument came from an unexpected place, not from the depths of Norwegian fjords or Icelandic beaches, but from the waters of the English Channel between France and England. In 2002, a team of underwater archaeologists was investigating the remains of a shipwreck dating to approximately 1592, located off the coast of Alderney, a small island in the Channel Islands archipelago. The vessel of English origin had succumbed to a storm. Among the objects recovered from the seabed, researchers found a translucent rectangular crystal, approximately 7 centimeters long. When subjected to mineralogical analysis in the laboratory, the crystal revealed itself to be a high-quality specimen of Iceland spar. What made the discovery even more significant was the context. Beside it, in the same compartment of the ship, were other navigational instruments of the time, including a circular disc whose marking suggested it had functioned as a primitive form of solar compass. This physical association, the calcite crystal deposited side by side with recognized navigational instruments, transformed what was until then an intriguing hypothesis into something much more concrete and verifiable. If English sailors of the late 16th century were still carrying this mineral on board as a navigational aid, the probability that the technology was much older, dating back perhaps to the Scandinavian navigators 6 or 7 centuries earlier, became difficult to ignore. The discovery of the Alderney crystal did not end the scientific debate, but it intensified and redirected it. To transform the hypothesis into a conclusion accepted by the scientific community, it was necessary to demonstrate experimentally, with methodological rigor, that Iceland spar could function as a navigational instrument in the real conditions of the North Atlantic. This demonstration was carried out by a group of European researchers, notably through the work of physicist Guy Ropars and his colleagues at the University of Rennes, in France, published in a series of studies starting in 2011. The experiments were carefully designed to simulate the conditions a Viking navigator would face in the open ocean. Researchers tested the ability of Iceland spar to reveal the sun's position under partially cloudy conditions, evaluated the method's precision at different solar elevation angles, and compared the results with actual values measured by modern precision instruments. The results were revealing. Under favorable conditions, the Iceland spar method allowed for the determination of the sun's position with a margin of error of only 1 or 2 degrees. In an ocean where a single degree of deviation in the route can accumulate a positioning error of dozens of kilometers over a journey of several days. This precision is remarkable for an instrument built entirely from materials available in nature, without industrial processes or artificial technology of any kind. A subsequent study, published in 2013 in the scientific journal Proceedings of the Royal Society A, one of the most prestigious scientific publications in the world, considerably deepened the analysis. Researchers including Denis Zarhegi, Albert Lefloch, and collaborators assessed with statistical methods the proportion of time during which polarized light would be detectable even under substantial cloud cover on typical Viking routes. The conclusion was that Iceland spar would be effectively usable for a significant portion of a sailing journey, enough to allow for frequent course corrections and the maintenance of a reasonably accurate trajectory throughout multi-day crossings. The researchers also identified a particularly favorable aspect. The method works best precisely when the sun is near the horizon, that is, in the early morning hours and late afternoon, the moments when conventional navigation by the sun is most difficult. The sunstone filled this gap in a remarkably elegant way, being most useful precisely when other methods were least reliable. Iceland spar was, however, just one instrument within a much broader system of nautical techniques and knowledge that the Vikings developed over centuries. One of the most fascinating archaeological findings related to this nautical culture is the Unartok disc, discovered in 1948 during excavations at a medieval monastery in southwestern Greenland. The object, partially preserved and made of wood, is in the shape of a semicircle with notches and markings on its edge. Subsequent investigations, including work by researchers at the Vienna University of Technology, concluded that it was likely a solar compass, an instrument that, with a central pin casting a shadow over its markings, allowed the navigator to determine the north-south direction and estimate their latitude. Experiments with functional replicas demonstrated its efficacy in the conditions of Arctic latitudes, especially during long summer days. Combined with Iceland spar, it would form a complementary navigation system, one instrument for when the sun was visible, the other for when the sky was overcast. In addition to these instruments, the Vikings employed constant latitude navigation. By keeping the North Star always at the same height above the night horizon, the navigator ensured they were following the same line of latitude, advancing east or west without significant deviation. This method is particularly effective for the Vikings' transatlantic routes, which often followed specific latitudes. The route between the western coast of Norway and Iceland, for example, follows approximately between 61 and 65 degrees north. To estimate the altitude of the North Star, navigators likely employed simple methods. The extension of the arm with a clenched fist corresponds to an elevation of approximately 10 degrees for most adults. With enough practice, an experienced navigator could estimate their position with good precision, using only their own body as an instrument. All this repertoire of nautical knowledge was not recorded in technical manuals. It was transmitted orally, from generation to generation, embodied in songs and poems, and above all passed from master to apprentice during the voyages themselves. A young man embarking on his first expedition as a rower was simultaneously beginning an apprenticeship that could last for years. Observing how the most experienced navigators read the sea and the sky, learning to recognize the signs that they had learned from those who came before them, these youths incorporated a legacy of empirical knowledge that was, in its essence, a practical science transmitted live, without a laboratory but with the entire ocean as a testing ground. It is tempting, and at the same time erroneous, to think of this tradition of knowledge as something intuitive or mysterious. What the Vikings did was fundamentally applied science, systematic observation, identification of recurring patterns, and the formulation of practical rules based on repeated experiences verified under real conditions. The efficacy of this body of knowledge manifested itself concretely in the achievements of the Viking expansion throughout the 10th and 11th centuries. Iceland was reached by Norwegian adventurers around 860 and 870, and permanent colonization was consolidated around 874, with Ingolfur Arnason frequently cited by the sagas as the island's first permanent settler. Greenland was discovered and settled by Eric the Red around 985, following his temporary exile from Iceland. During the 3 years he spent as an exile, Eric systematically explored the coasts of the immense island, mapping its fjords and its resources with remarkable method and determination. Around the year 1000, Leif Erikson, son of Eric, raised in the dual cultures of Iceland and Greenland, and an experienced sailor since his youth, led an expedition that reached the coast of North America, in a place the sagas call Vinland, the land of vines. This journey was neither an accident nor a fortuitous drift. It was an intentionally planned expedition based on information Leif had obtained from other sailors who had sighted unknown lands to the west of Greenland. It was a deliberate voyage, conducted by a navigator who knew how to get there and, just as importantly, how to return. The definitive archaeological proof of the Norse presence in pre-Columbian North America came in 1960, when the Norwegian explorer Helge Ingstad and his wife, the archaeologist Anne Stein Ingstad, discovered the ruins of a settlement on the northern tip of the island of Newfoundland in Canada at the place called L'Anse aux Meadows. The excavations revealed the foundations of turf buildings, metal tools, and other artifacts consistent with the Norse material culture of the 10th and 11th centuries. Radiocarbon dating confirmed that the structures had been erected around the year 1000 of the Christian era. L'Anse aux Meadows was recognized as a UNESCO World Heritage Site in 1978 and remains to this day the only confirmed archaeological site of a Norse settlement in the Americas. It demonstrates irrefutably that the Vikings reached the American continent approximately 500 years before Christopher Columbus, through intentional and planned navigation along routes they had identified and traversed systematically. Why the settlement did not become permanent is a question that the sagas address in a suggestive way. The texts mention conflicts with the native peoples who already inhabited those lands, the Skraelings, as the Norse called them, and the difficulties of maintaining a viable colony at such a great distance from supply centers in Greenland and Iceland. The most widely accepted theory today is that the combination of these two factors, the resistance of local peoples and the insufficiency of available human resources, made the project unfeasible with the means available at the time. What the history of the Solestein reveals to us, therefore, goes far beyond the mechanics of a navigation instrument. It tells us something profound about the relationship between practical knowledge and theoretical understanding, between patient empirical observation and formal scientific explanation. The Vikings who used Iceland's spar to find the sun beyond the clouds knew nothing about light polarization, Rayleigh scattering, or the wave physics that Huygens would begin to describe mathematically at the end of the 17th century. They did not need to know. They knew the stone worked, and that practical knowledge was enough to cross oceans, reach continents, and change, however silently, the history of human exploration of the planet. The interval between practice and theory was particularly striking in this case. The Vikings used the sunstone around the 10th century. Double refraction was formally described by Bartholin in 1669, approximately 7 centuries later. The relationship between this phenomenon and the polarization of light was explained by Huygens in 1690. And the experimental confirmation that Iceland spar could effectively function as a solar navigation instrument only arrived in the early 21st century, with the work of Ropars and his collaborators. Approximately 11 centuries separate the practical application from the complete scientific confirmation, a hiatus that invites reflection on what other ancient practical knowledge still awaits formal understanding. The history of the solar stein challenges us to question the stance we often adopt toward the past. For many decades, the reference in the sagas was marginalized, treated as a folkloric element without verifiable substance. It took a combination of underwater archaeology, mineralogical analysis, and rigorous experimental physics to finally confirm what medieval narrators had described with disconcerting precision. Iceland occupies a singular place in this narrative, which goes beyond the mere availability of the mineral. The island was the central geographical hub of Viking navigation routes. From Norway, vessels departed for Iceland. From Iceland, they headed to Greenland. From Greenland to the coasts of North America. And it was in this volcanic land that the Norse society that would produce the sagas flourished, and which was the first to establish a parliamentary form of government in Europe, with the Icelandic Althing founded in 930, often cited as the oldest functioning parliament in the world. The same historical processes that generated the technology of the solar stein also generated a political culture of remarkable sophistication. Two legacies of a single civilization that learned to navigate the world in every sense of the word. When today we look at a cloud-covered sky and resign ourselves to not seeing the sun, it is worth pausing for a moment to imagine, at some point on these same cold seas, approximately 1,000 years ago, a Viking navigator would extend his arm, retrieve a transparent stone from a compartment on the vessel, and raise it toward the uniform grey of the sky. And he would see, in that apparently impenetrable grey, the subtle signature of polarized light, the invisible signal that pointed to the hidden sun. He would then adjust the rudder of his nar, mentally recalculate his position in the immense ocean, and continue onward toward a destination that only he, at that moment, knew with precision where to find. There is something profoundly moving about this image, not just because it connects us to a distant past and to people who lived lives radically different from our own, but because it reminds us that the human capacity to observe the world, to find patterns where others see only chaos, and to develop creative solutions to apparently insurmountable problems was not invented by modernity. It is as old as humanity itself, present in every era and in every culture that had the courage to look at the horizon and decide that there was something beyond it worth reaching. The solar stein, the sunstone, is more than a medieval navigation instrument. It is a symbol of the profound relationship between human observation and nature, between practical knowledge and possibility, between humility in the face of what is not yet understood and boldness in the face of what must be discovered. It is a reminder that the boundary between the possible and the impossible is much more porous than we usually imagine, and that often to cross it, one only needs to know where to look and have the patience to learn to see what is right before one's eyes. If this story has awakened in you the same fascination that still moves researchers today, who dedicate entire careers to unraveling the mysteries of the past, then you already hold your own solar stein in your hands. Like this video. It is the crystal that shows us the way and tells us that stories like this matter to you. Subscribe to the channel, because there are many other oceans of history waiting to be crossed together, each with a secret kept, waiting for curious and attentive eyes. And leave in the comments what surprised you most on this journey. Was it the physics behind the sunstone, the silent audacity of the Atlantic crossings, or the discovery at Lanceau Meadows that proved what the sagas had described for centuries? Your voice is part of this navigation, just as every Viking navigator depended on the voices of those who had already crossed those waters before. We navigate guided by your choices. See you in the next video.